But when it is 0, y must be 3 over 2. Therefore, whenever y is equal to 3 over 2, this complex number will be purely imaginary number or simply imaginary complex number. Okay, that's it. The next one, question number 8. A, given z1 is equal to this one and z2, and we are asked just to find the modulus or the norm of z1 plus z2. We can approach different approaches or simply procedure for finding this one, but let us see how we can find the norm of z2, the sum of these two complex number. First, let's add them together. That is z1 plus z2 is equal to the absolute value of 2 plus 3i, that is simply for z1, and 3 plus 2i for z2, which is equal to 5 plus 5i. Then the norm of the sum of these two is said to be the norm of their sum, that's 5 plus 5i, and this could be the square root of 5 square, that is the square of the imaginary and the real part of this complex number, that is 5 square plus 5 square is 50. And when we further simplify this one, it could be 5 radical. Therefore, the sum. Okay. The next one could be, given z1 is equal to this one, we have 3 complex numbers. Then after we are given these 3 complex number, we are asked just to find w in terms of a and b in the form of x plus ii, where w is equal to z1 times z3 over z2. Just simplification. So to do this, first let's find z1 times z3. Or let us substitute that simply z1, z2, and z3 like this. And we have this one that's simply 2 plus 3i. That is z1 times 3 plus 2i multiplied by this one over this. That means this could be just to make this one simply just to live, or just to make this one into real, we have to multiply both the numerator and denominator of this one by the complex conjugate of this one. So that is this fraction. Then this could be, after simplifying this one multiplication and this one even, and further simplification we have, we can obtain this one, that is w is equal to 6a plus 4b over 13 plus 5a minus 12b over 13. So that this one 6a plus 4b over 13 is said to be the real part of w, which is z1 times z3 over z2, and 5a minus 12b over 13 is said to be the imaginary part of this one, that's simply w, when w is z1 times z3 over z2. The next question is question number 8c. That means just finding the argument of w in radian measure whenever w is given to be 17 over 13 minus 7 over 13. We know that the argument of a given complex number is obtained by the tan inverse. That we know that the argument of a given number is, or simply complex number is, it is an angle which is formed in between the positive x-axis and the axis, or simply the arrow determined by the complex number itself. Therefore, this is an angle that simply, if the angle is that one, then it could be arctan, or simply tan inverse of the imaginary part of the complex number divided by the real part of the complex number, that is minus 7 over 13 over 17 over 13. So that this could be tan inverse or arctan of negative 7 over 17, which can be approximated to negative 0.391 rad. This is negative because this is something, the angle, that is the terminal side of the angle, will be found in the fourth quadrant, so that because the argument is an angle between the positive x-axis and the axis, or simply the array of the complex number itself, so that it is the negative angle. The next question number 9. Find the modulus and argument of z, w, zw and z over w if z is equal to 1 plus I and w is equal to radical 3 plus I. And you are asked just to put your observation at the last. And therefore, here, what we are given here is we are given about two complex numbers z and w, and we are asked just to find the modulus and argument. We know that the first, the modulus, the modulus, yeah, the norm of z is equal to radical 2, which is the square root of 1 square plus its imaginary part, that's 1 square. And its argument will be tan inverse of 1 over 1, that's simply tan inverse of 1, which is pi over 4. Similarly for w is given to be radical 3 plus I, so that it is norm, or simply modulus could be the square root of the radical 3 square plus 1 square, which is the square root of 4, that's simply 2, since norm is positive. And its argument will be that's the angle between the positive x-axis, and its array will be tan inverse of 1 over radical 3, or arctan of 1 over radical 3, which is pi over 6. And their product, that simply z times w could be, that is their norm first. The norm will be, that is 2 radical 2, which is the product of norm of z times norm of z. And its argument, or simply will be the argument of the product of two complex numbers, is simply the same as the sum of the arguments of the individual complex numbers, so that pi over 4 is the argument of z, and pi over 6 is the argument of w, so that it is just 5 pi over 2. Similarly, the last one, z over w, that is first the norm could be radical 2 over 2, so that this radical 2 over 2 means the norm of the quotient of two complex numbers is said to be the quotient of the norms of the individual, so that radical 2, which is the norm of z, and 2, which is the norm of w, so that it is just radical 2 over 2. And the argument is also what? The argument of the quotient of the complex number is the same as the argument of z minus the argument of w. So that is just equivalent with, pi over 6. I think this must be minus. That means this is minus pi over 6. So that in this case, we have the difference between these two, which is pi over 12. Pi over 12, so that this is the difference. Therefore, what we can observe here is that the modulus and argument of the product of two complex numbers is here to be the product of their corresponding norms, and their argument is the sum of the individual complex numbers. And for the quotient, the norm of their quotient is the quotient of the individual norms, and their argument will be the difference between the arguments of the two. Question number 10. The complex number z is defined as z is equal to I into 1 plus I multiplied by 1 minus 2i squared. It is further given that z, the complex conjugate of z minus 3i plus p of z minus 3i is equal to k of z bar, where p and q are real constants. Find the values of p and q. That means we are asked just to find the values of p and q, which are real constants, satisfying this conditional simple equation. That means. So first, let us compute z. Z is given to be here. So let us multiply z. Simplify z, so that z is equal to the simplified form of this expression, which is directly taken from this one. And it could be 7 plus I. When we simplify this one, that's simply squaring. After squaring it, if we multiply 1 plus I with 1 minus y squared, it is exactly 7 plus I. Then a given equation or simple equation, that simply if we substitute it here, we have 7 plus 2i plus p of 7 minus 2i is equal to q of 7 minus I. Q of 7 minus I means the complex conjugate, because it is z bar, z this one, so that it becomes 7 minus I. And this could be 7 plus 2i could be, when we substitute z, that is 7 plus I here, we have the imaginary part of this one, that simply, the real part is 0, so that we have 7 here. Then we have I here, I minus this one, that's simply 3. After taking that, simply it becomes a minus 2, and its complex conjugate could be positive 2. Then after writing this one, we have the following system of equation, that is from equating its real and imaginary parts. From the real parts here, we have the real part from this one, that's simply 7 plus 7p is equal to 7q. And from the real part, we have twice of I minus twice of p. When we distribute this one over here, it is just minus q. Then solving this system of linear equation, we have the values of p and q, that is simply p is equal to 3 and q is equal to 4. Then whenever p is equal to 3 and q is equal to 4, this equation, that is z minus 3i bar plus p of z minus 3i, becomes q of z bar, when z is this expression, or 7 plus I. The next one is question number 11. Again, it is solving, that is for find the element of the complex number in the form of x plus iy, where z bar is equal to x minus iy if z is equal to, z minus 8 is equal to I into z minus twice of z bar. Then in order to write or simply have a solution for this one, let z is equal to x plus y, so that its complex conjugate would be x minus iy. And then, sorry, x minus 8 plus iy is equal to 8y minus ix. That means if you substitute this one, that simply we have z minus 8, we have this one, that means, so that it becomes x minus 8 plus iy is equal to y minus ix. Then equating the real and the imaginary parts as usual. We have the real part of this one is x minus 8, and the real part of second one is 8, so that we have x minus 8 is equal to y, and the imaginary part will be, that is y is equal to this one, that is minus x. So that's solving the system of linear equation. We have x equal to 4 and y is equal to minus 4. That's just if you substitute minus x in the place of y here and take to this one, it becomes 2x is equal to 8. Dividing both sides by 2, we have 4 for the value of the first variable x. And after obtaining this one, one is the negative of the other, so that if x is 4, y becomes negative 4. Therefore, after obtaining this one, the form of the complex number could be z is equal to 4 minus 4y, that in the form of x plus iy. Question number 12a. Express the following complex number in polar form. Polar form, that means writing the expression or simply the given complex number as a function of r and theta, where r is its modulus and theta is the argument. Just to do that, first we have to simplify this one or convert this one into standard form of complex number, that is z is equal to x plus iy. Then when we simplify this one, that is 3 minus I over 2 plus I. When we multiply both denominator and denominator by the complex conjugate of 2 plus I, that is 2 minus I, we have 1 minus I. Then when we square it, that means the square of this one, 1 minus I, is equal to minus 2I. So that, let's write this one into polar form. In order to write the polar form of this expression or simply given complex number, we need to have two things. That simply the norm, that is R, and the argument, that's simply theta. Simply the R could be the square root of, since the real part is 0, that is the square root of minus 4 square, that is 4, which is 2. And theta could be, that is tan inverse of minus 2 over 0, which is undefined. Whenever tan inverse of, we know that tan inverse of an angle theta is undefined whenever theta is either negative pi over 2 or pi over 2. But in this case, it is negative pi over 2 because the terminal side of this one, or simply this point, is found on the negative imaginary axis. So that theta is negative pi over 2. Therefore, using this one, the polar form of the given complex number could be 2 times, that's simply R, cosine of negative pi over 2 plus I times negative sine of negative pi over 2. So that this is the polar form of the given complex number. Next one is express the following complex number in polar form. Again, it's the same, but with a little modification of simply complexity here because of the existence of this one, that simply the square is just the denominator. So as usual, first let us simplify this one, this expression, or this complex number in standard form. When you do this, first we have to simplify the denominator. So that 1 plus 7I over 3 minus 4I, that is the square of 2 minus I is, I think, 3 minus 4I. And then when we multiply again this one both sides by the complex conjugate of this one, we have obtained minus 1 plus I. So that the polar form would be, as usual, as we have seen previously in the previous question, in order to write the polar form of this complex number, we have to determine its modulus and the argument. The modulus is the square root of minus 2 square plus 1 square. I think that's radical 2, and its argument will be tan inverse of, or arctan of 1 over minus 1, or simply minus 1, which is negative, that is simply negative, positive 3 over 4, which is in the second quadrant. Therefore, R is this one, theta is this one. Therefore, the polar form of this complex number could be radical 2, which is R, cosine of 3 over 4, that is the argument, plus I times sine of 3 pi over 4. Therefore, this is the polar form of this expression, or its simplified form, which is minus 1 plus I. Okay, the next one, that's question number 13a, is finding the argument and the principal value of the argument there. We know that the argument is the angle between the positive x-axis and the terminal side determined by the complex number itself. So that to do that, first we have to simplify this expression. That is, we have to change it into a standard form, that is, which is suitable for knowing its real and imaginary part. Therefore, the simplified form of this one, that is when we multiply both the numerator and the denominator by the complex conjugate of the denominator, which is 1 minus y, that is 1 plus 2i. We have this one, that is 7 minus I over 5. This is 5 because it is the square of the norm of 1 square minus 2 square, or the product of this complex number by its complex conjugate. And then the principal, or simply the argument, could be, that is arctan or tan inverse of the imaginary part of this one, that is minus 1 over 5 divided by 7 over 5, which is minus 1 over 7. And this could be approximated using that of calculator, scientific calculator. We can approximate this one as negative 0.1419 rad in radian measure. That means this is for the quadrant angle. That is why it is negative. And the next one, that's question number 13b. Find the argument again and the principal value of this one. That's simply this expression. As usual, let's first simplify it, so that the simplified form of this thing could be, that's -2. That means we have to change first individually the fractions into standard form, and when we add them together we can obtain -2i, so that the principal or the principal value or the argument of this one could be tan inverse of -2/0, because the real part of this simplified form of this expression is 0, so that the argument that simply theta could be -pi/2, which is a negative angle. So that this could be approximated as -3.14, which is -3.14/2, something like that. You can approximate it, or even we can put it like this in radian measure. Next is the same question, that finding the argument and principal value again. Again, we have to multiply or simply simplify first. The simplified form could be this one, that is 1 minus radical 3i times 1 minus I could be this one, that is 1 minus radical 3 minus 1 plus radical 3i. That is, this is the real part, and this one is the imaginary part of the simplified form of this expression. Therefore, the argument or the principal argument of this one could be tan inverse of -1 plus radical 3 over 1 minus radical 3, which could be approximated as 5pi/12 rad. I can use scientific calculator. That is tan inverse of 1 plus radical, -1 plus the negative of 1 plus radical 3 over 1 minus radical 3 is 5pi/12 rad. The next one, that is we're approaching to the need. Proof using de Moivre's rule, our theorem. Cosine of 2 theta plus I times sine of 2 theta over cosine of 3 theta plus I times 3 theta is equal to cos theta minus I sine theta. So to do this, we have this one, that is the first one, or simply denominator, cos 2 theta plus I sine 2 theta, means using de Moivre's or simply Euler formula, we have cos theta plus I sine theta, or simply z square. If we take z is equal to cos theta plus I sine theta, I sine theta, and the denominator could be cosine of theta plus I sine theta, the power of 3. Then when we take this one, that's simply minus this one, that's simply 2 minus 3, we have cos theta plus I sine theta, the power of -1, which is equal to 1 over cosine of theta plus I sine theta. Then when we change or simplify this one in standard form, we have to multiply the numerator and the denominator of this one by the complete conjugate of cosine of theta plus I sine theta, so that it is just cosine of theta minus I sine theta, because the complete conjugate of cos theta plus I sine theta, when we multiply this one denominator by 1, it is just this one, and cosine of theta plus I sine theta multiplied by the complete conjugate of this one could be, that is cos square theta plus sine square theta, which is 1, trigonometric identity. So that becomes cos theta minus I sine theta over 1, or cos theta minus I sine theta. Therefore, this is how we can approach just to prove this expression. The next one is similar to the previous one, I guess, again on the application of de Moivre's theorem. That is proof using de Moivre's theorem that cos 3 theta is equal to cos cubed theta minus 3 cos theta times sine square theta. So just to prove this one, we have to expansion of this one, that is a plus cubed. A plus b cubed is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. So let's let us expand this one, that's cos theta plus I sine theta, the power of 3. This could be the cubed of the first one, that's cos cubed theta, 3 times a squared, that's cos squared theta, multiplied by b, that's simply I sine theta, so that's 3i cos squared theta sine theta, minus, why minus here? Because 3a means a is b, so that's 3 times cos theta, but b squared, that is when the square of I sine theta could be the square of I is minus 1, sine theta is sine square theta, so that minus 3 cos theta times sine square theta, minus I sine cubed, that is the cube of I sine theta, the cube of I is minus I, the cube of sine theta is sine cubed theta, therefore there is cos cubed theta plus 3i cos square theta sine theta minus 3 cos theta sine square theta minus I sine cubed theta. Then the real part of this one could be, that is cos 3 theta, that is the real part. Cos 3 theta is equal to, from this one, the real part of this expression, that is we have cos cubed theta plus, minus 3 cos theta sine square theta, but the rest, this and this one, that is I sine cubed theta, are imaginary. Therefore, cos theta could be cos cubed theta minus 3 cos theta sine square theta. Therefore, this is the proof. Question number 14c, prove using the Moivre's theorem again. Z to the power of n plus 1 over z the power of n is equal to 2 cosine of n theta, where z is equal to cos theta plus I sine theta. So if we are given z is equal to z to be this one, so that z to the power of n, by using that of the formula, we have z to the power of n is equal to cos n theta plus I sine n theta. Similarly, 1 over zn could be 1 over zn means 1 over z to the power, z to the power of minus n. If we substitute minus n in the place of n here, we have cosine of minus n theta, but since cos theta is an even function, cosine of minus n theta and cosine of n theta are the same. Therefore, it becomes like this, and sine of minus n theta is identical with the negative of sine of n theta, since it is an odd function. Then when we add these two together, just to bring this expression, we have zn plus z to the power of n plus 1 over z to the power of n, cosine of n theta plus cosine of n theta, twice of cosine of n theta, but this will be cancelled. That is I sine theta, I sine n theta plus minus I sine theta will become 0, so that z the power of n plus 1 over z the power of n is equal to only twice of cosine of n theta will be left. Okay, question number 15. Given that p and q are real and that 1 plus 2i, the root of the equation z square plus p plus 5iz plus q of 2 minus i is equal to 0. Determine the values of p and q, be the other root of the equation. So we are asked just to find the two equations here. So the solution would be, let z is equal to, substitute z is equal to 1 plus 2i here in the place of z here. Then it becomes p plus twice of k minus 13 plus I of twice of p minus q plus z, 9 plus is equal to 0. And then equating the real and the imaginary parts together, because the first expression closed by the first bracket is the real part, and this one is, that is 2p minus q plus 9 is the imaginary part, so that we have this equation, that is p plus 2k is equal to 13, because it is 0. 0 plus 0, that means 0 plus 0 I, that means, and 2p minus q plus 9 is equal to 0, or 2p minus q is equal to minus 9. So that if we solve this system of linear equation, we have p is equal to minus 1 and q is equal to 7. Therefore, if we substitute p is equal to minus 1 and q is equal to 7, this equation will be satisfied whenever z is equal to 1 plus 2i. And the other root of that is 4p. The other root of the given equation could be sum of roots, that is sum of the two roots. That means the negative of p plus 5i is equal to, which is equal to 1 minus 5i. 1 minus 5i. That is because p in this case is minus 1. So that if you substitute minus 1 for p here, minus 1 plus 5i, which is negative, when we distribute negative there, minus of minus 1 plus becomes plus 1 and positive 5 becomes negative. Therefore, the other root could be 1 minus 5i minus of, that's simply z. This combination, that is z 1 plus 2i, which is equal to 7i. That is 1 minus 1 is 0, minus 5i minus of 2i is equal to negative 7i. Therefore, the other root of the previous equation. 16. Find z, an element of complex number, and plot the result in the Argand plane, or that is the imaginary complex plane, if z to the power of 4 is equal to 1. That is the extraction of root. Solution will be, we have for the extraction of root, we have the formula that is equal to cosine of 2k pi over 4, when 4 is the exponent here, and I times sine of 2k pi over 4 when k is running from 0 to that of 3. That's a random of, 0, 1 to 3, so that it will have 4 roots. Therefore, individually, when k is equal to the first one, that's simply 0. If you substitute k0 here, we have z naught cosine of 0 plus I times sine of 0. Cosine of 0 is 1, but sine of 0 is 0, so that z naught will becomes, I think, 1. Z naught is 1. And when you take k to be 1, if you substitute 1 here, it becomes z1 is equal to cosine of 2 pi over 4 plus I times sine of 2 pi over 4, or simply pi over 2 pi over 2. Cosine of pi over 2 is, I think it is 0, but sine of pi over 2 is 1, so that it is just z1 could be, there is 1, that is 1 times I, that is I. Similarly, for the second one, that's simply in order to determine z2, or the third root of this one, we have to take k to be the third element, that's simply 2. If we substitute 2 here, we have 2 times 2, that's simply 4 pi over 4, that is cosine of pi plus I times of pi. Cosine of pi is 0. Cosine of pi is, I think, minus 1, but sine of pi is 0, so that it is a real part, that is simply z2 is minus 1. And the third one could be whenever k is 3, it becomes, when k is 3, 2 times k, that's 6 over 4, or 3 over 2 pi plus I times sine of 3 over 2 pi. But 3 over 2 pi is sine of 3 over 2 pi is 1, and this one cosine of this value is 0. Therefore, it is purely imaginary. Therefore, it is z3, that is minus I. Therefore, the 4 possible roots of this equation could be 1i minus 1 and minus I. We know that, for example, here I is the root of this one. It is complex conjugate, that is z3, which is minus I, is also the root of this one. The same holds true for z0 and z2. Then the plotting for this one could be that when z0 is this one, that's simply 1, purely on the real axis, and z2, it is minus, positive I on the positive imaginary axis. this is I, and z2, which is -1 on the real axis, z2 -1 on the horizontal axis here, and the last one, that's simply z3, will be -I on the negative imaginary axis. Therefore, there is a circle, that is a unit circle, whose distance for whose center is at the origin. That's simply the origin of the imaginary and the real axis. Okay, the next one, that's question number 16b. Again, it is similar to the previous one. Find z an element of C and plot the result in Argand plane if z cubed is equal to -3. We expect 3 points or simply roots for this equation, and the equation will be obtained by using the previous formula. That the formula is twice of k. Z is equal to 2 times cosine of pi plus twice of k pi over 3 plus I times sine of pi plus twice of k pi over 3, when k is 0, 1, and 2. Then for k is equal to 0, we have z denote, that is, z denote is equal to cosine of the 0, that is pi over 3 plus I times sine of pi over 3. Cosine of pi over 3 is cosine of pi over 3 is I think 1, and sine of pi over 3 is radical 3. Therefore, the combination could be z denote 1 plus radical 3. And z1, that is when k is equal to 1, it could be cosine of, that is z1, 2 times cosine of this one, that's simply pi plus 2 pi over 3 plus I times sine of pi plus 2 pi over 3. And this could be, that is cosine of pi plus 2 pi over 3 is -2, I think -1, and -1 times this one, that's simply 2, could be -2, but sine of pi plus 2 pi over 3 is already 0, so that it is real, it becomes -2. Similarly, when the last one, k is equal to 2, 2 times cosine of pi plus 2 times 2, that is 4 pi over 3, which is 5 pi over 3 plus I times 5 pi over 3. Therefore, it could be cosine of 5 pi over 3 could be, that is, I think, 1 over 2, and sine of 5 pi over 3 could be negative radical 3 over 2. When we multiply both sides by 2, we have 1 minus radical 3i, so that we have 3 roots. These roots on the plot, or simply in the complex or Argand plane, could be z denote is around here 1 plus radical 3i, and z2 is on the negative real axis, that is -2, and on the fourth quadrant, that is simply z2 is 1 minus radical 3i, so that this is the root of z cubed is equal to -8. Similarly, the last one, I think it is the last, that is, it is similar to that one. I think it's better if I left it as an exercise for you. By the way, the roots are here, but you are required to try to plot the roots on the Argand plane. Okay, that is the end for the solution.